Good morning, ladies and gentlemen. It is my pleasure to open this session with the first Earth Explorer 12 candidate, Hydroterra Plus. Water is the foundation of life, agriculture, ecosystems, energy production. And Hydroterra Plus starts from a simple but powerful question. What if we could observe the water cycle as it happens on timescales of hours? Hydroterra Plus is based on a persistent regional observatory for scientifically and societally important areas within Europe and Africa, and opens a new window on sub-daily water dynamics. It provides a simultaneous view of key water cycle elements using a synthetic aperture radar in geostationary orbits that is able to imagine over a continental scale. Now, before going to the mission itself, I would like to acknowledge the large community effort behind this mission. More than 100 people work in the phase 0 of Hydroterra Plus under the advice of the Mission Advisory Group, who is sitting here today. The Mission Advisory Group is composed by Andrea Montiguarnieri, Alberto Moreira, Antonio Parodi, François Boutier, Harald Kustmann, Juan Manuel Lopez Sanchez, Steven Hobbs, Juha Lemettinen, Luca Brocca, Thomas Nagler, Tim Bright, Vasiliki Kotroni, and Peter van Ovelen. My name is Christian Rossi, and together with Andrea Sita, we are overseeing this mission from ESA side. The ESA core team is also sitting here today. Now, with that, and that was brief, I'd like to introduce on stage Harald Kustmann, who will tell us why Hydroterra Plus is scientifically compelling.
Thank you very much, Christian. Ladies and gentlemen, the availability of water in sufficient quantity and quality determines our life on Earth. Water is a prerequisite for ecosystems and us humans. It regulates climate, e.g. via plant and soil evaporation, and it is crucial for public health, as we need it for cooling in times of extreme heat, as we have it recently throughout large parts in Europe. We need it for electricity generation with hydropower, and we need it for rain-fed and irrigated agriculture, and thereby our food security. And there are dramatic changes happening in recent decades with our water cycle. There is evidence, both from ground observations and from space, that larger parts of Europe lose water. The GRACE satellite mission observed declines of soil water columns up to 20 millimeters a year. So, significant less water is available year by year. We need to cope with this phenomenon of not enough water. Currently, in large parts of Europe, we do have a significant precipitation deficit, and together with the heat wave, there is around 30% of land in Europe under drought conditions, according to the European Drought Monitor. And on the other hand, we must cope with the problem of too much water. Let us remember the catastrophic flood in the province of Valencia 2 years ago that has caused more than 150 deaths. Not yet enough water and too much water, that are the big hydrological extremes, and they have significant economic costs. For example, just for the right side, the big flood in Germany 5 years ago, the R, has cost around 29 billion euro. This one event has caused damages which is nearly double as much as Germany spends in research per year. And it is more than Germany has spent in defense per year before the war. Even when it appears that climate and environmental issues are not anymore in the focus of people in recent years, this is misleading. When we have a look in the global risk report of the World Economic Forum in Davos, where more than 1,300 experts worldwide give their opinion on ranking of risks, we see their long-term perception of risks. The report concludes on extreme weather events as the most problematic risk. Further, water-related risks like biodiversity, changes in Earth system, and natural resource shortage, they are also always fully water-related. They are in top 6. And it might be less known that also in the big climate conference, the World Climate Summits, the so-called COPs, the Conference of the Parties, they mention clearly, they emphasize the need to address existing gaps in the climate observing system, and water, of course, is one of the crucial observations, and they also request much better implementation of early warning for all. So Hydroterra Plus is in line and justified by significant, so to say, global documents. Hydroterra Plus does not only address Europe, it addresses by purpose the African continent. Why? Because it is particularly threatened by climate extremes like floods and droughts, and this endangers subsistence agriculture. And it is still a very data-scarce region of the world. This figure here shows the number of stations, climate stations, declining. While this is an older study from 2012, this is still valid and even worse. You may say, we already do have satellite systems in orbit that deliver water-related information, like SMOS, Sentinel, SMAP, Meteosat, for example. Yes, that is true, but they do have a critical gap. We urgently need sub-daily observations, because it is the sub-daily timescale where intense storms develop, where we have rapid changes in soil moisture and snow water, and where irrigation happens. Let us have a closer look on the spatial and temporal scales of water challenges. It is from timescales from hours, days, weeks, and spatial resolutions from hundreds of meters till hundreds of kilometers, where mesoscale convective systems, storms, irrigation take place. And when we look at the spatial temporal extents of flooding and droughts, earthquakes, volcanic eruptions, and landslides, in total, and compare how far current observations and satellites in orbit address this window, we see it does not really fit. And it is Hydroterra Plus that intends to fill this gap in this current observation gap. So, the focus of Hydroterra Plus is on altogether 6 variables. It's on integrated water vapor, it's on surface soil moisture, it's on snow water equivalent, it's on snow melt phase, it's on line of sight ground displacement, and it's about hazard change map. Let's start with integrated water vapor. What is that? IWV. That is the amount of water in an atmospheric column given in kilogram per square meters, or simply a water column in millimeter or centimeter. High values of the integrated water vapor combined with rapid upward movement of moist air is a precondition for intense convective rainfall. The evolution is highly sensitive to atmospheric moisture and is coupled to land surface processes. And it is a key variable for improving the understanding and forecasting of intense rainfall. Yes, and it reorganizes through the day. And that is why we need to learn and see the sub-daily processes. We need the sub-daily observations to capture the build-up, the convergence, and the rapid transitions. And if we have this value, they can be assimilated nicely into numerical weather prediction models, and then they allow us to improve the predictability of storm organization and heavy precipitation. The second variable, surface soil moisture, that is the water contained in pore spaces between soil particles, measured as a volumetric water content in cubic meter per cubic meter. Surface soil moisture is a hinge variable linking rainfall, infiltration, runoff, evapotranspiration across the land surface and the subsurface. And it is essential for improved assessments in agriculture, natural hazard, meteorology and climatology. And I show you this picture of a very fancy soil moisture measurement on ground, cosmic ray neutron sensing, and that is established in North Ghana in the Volta region. And that is why we also go for the Volta region later on, because we have very nice complementary measurements on ground. And again, here the sub-daily processes are decisive. They are necessary to capture the rapid wetting and drying, the irrigation and nighttime redistribution. And yes, it's the controlling variable for land-atmosphere exchange. The third variable is about snow water equivalent. This is the depth of a water column if the snowpack melts completely, measured in millimeters or centimeter. Water stored as snow is one of the major freshwater resources in our world. Snow melt can trigger rapid water release and flooding. And we know it has a very high spatial heterogeneity, and that also means we have still substantial uncertainties in its quantification. And it is not only the snow water equivalent, now it's also the melt phase, which means is it dry, wet, or refrozen, that we are going to observe with Hydroterra Plus. Because that is, the surface layer is subject to changes at this sub-daily scale. And this knowledge is essential for quantifying atmospheric and land surface atmosphere exchange process. And of course, it's critical input for the variety of all hydrological modeling. Last, in addition, we work on ground displacement and hazard change maps, because hydrological-driven hazards, they also can evolve within hours. As rainfall or snowmelt infiltration, they increase saturation, they raise pore pressures, and they reduce slope stability. And again, we need the sub-daily observations to detect pre-failure acceleration and to constrain failure times. So there's an added value for there's also an added value for non-hydrological hazards, for example, volcanic unrest, earthquake-related ground change. And that brings me to our science goals. We have 4 big science goals, and they are all about the advanced understanding. It's about the advanced understanding first of the atmosphere and sub-daily atmospheric processes, as they are important to better understand intense storms or extreme precipitation. The second goal is about the land surface and the terrestrial water cycle with all its crucial variables, particularly soil moisture. Then we have a clear focus on the cryosphere, because snow accumulation, snow melt, and the snow melt dynamics, that is a crucial variable to understand the water cycle. And finally, it's about the hazards and about ground motion and surface changes. Hydroterra Plus translates its science goals into repeated observations of atmosphere, land surface, cryosphere, and rapidly evolving hazards across large regional domains. And we have altogether 7 objectives within these 4 goals. The first, again, is on the atmosphere, and here it's on integrated water vapor, 2 kilometer sampling in 6 hours distance. about the land surface soil moisture, 1 kilometer sampling, 6 hours. The cryosphere, snow water equivalent and snow melt phase. And finally, ground displacements with samplings as short as 1 hour. All our Hydroterra Plus level 1 and 2 products and our mission objectives and scientific goals can be traced back to the ESA Earth observation strategy. There is a clear alignment to the overarching science themes and the guiding science questions of mission objectives. So that is all traced back to the Earth observation strategy. And let me illustrate this for one example, the example of surface soil moisture, which is crucial for improving our understanding of the land-atmosphere coupling and nearly all hydrological processes. So, coming from these 4 science themes, water cycle, energy fluxes, extremes and hazards, interfaces and coupling, ESA has defined very specific science questions. Here it is about coupling determinants, water cycle changes, and heat exchange. And heat exchange is always related to water. And that has defined our science goal to advance this understanding of the terrestrial water cycle, particularly for the surface soil moisture in sub-daily resolution. And again, our level 2 and level 1 products are clearly defined and can be traced back to the strategy. And with that, I hand over to my colleague Antonio Parodi, who focuses in the following more on the mission requirements.
Thank you, Harald. As he said, now I'm starting a journey into the Hydroterra Plus mission requirements. As already mentioned, Hydroterra Plus is a C-band radar in a geostationary orbit concept, and it has its own visibility region into the northern hemisphere. Associated to this visibility region, we have performed a pre-selection of initial selected area of interest which have certain specific characteristics. First of all, those areas of interest are representing contrasting hydroclimatic, cryospheric, and other related processes. Secondly, on the other hand, they are meant to address the mission objectives from different perspectives. The 4 initial selected areas of interest are reported in the figure on the right. They are corresponding to the Great Alpine region, to the Southeastern Mediterranean region, to South Spain and Atlas, and also we jump into the Africa continent to the Volta region. In order to arrive to this initial selection, we have adopted a set of 3 different criteria that I'm going to explore right now. The first driver has been based on a climate concept. We started from Köppen climate classification, and the idea has been to identify contrasting hydroclimatic conditions capable to cope with the complexity of the interplay between rainfall, water, soil moisture, snow processes from a perspective of water cycle. In this respect, we have considered Great Alpine region because it is representative of a mountain temperate climate. Conversely, the Southeastern Mediterranean region is representative of hot summer Mediterranean climate. In the case of South Spain and Atlas, we are moving to semi-arid Mediterranean conditions. And in the case of the Volta region, we are considering tropical savanna monsoon climate. All of those regions are considered in the literature from a scientific point of view also as climate hotspot areas. So they are also very important from the point of view of climate change. And this aspect is reflected into the fact that they are exposed to very critical natural hazards, getting more frequent and possibly more intense. We are speaking about floods, flash floods, wildfire, droughts, and just taking a journey in the visibility area, you may see that, for example, in the Volta region, there are phenomena like water scarcity, urban flood phenomena, moving close to the Mediterranean. In South Spain and Atlas, we are adding to the business wildfire and extreme heat. In the Gar region and Pyrenees, we are considering, on top of the previous hazards, also landslides, and in general, again, water scarcity. Southeastern Mediterranean is probably the richest one because it is including also volcanoes activities, earthquake, and coastal flooding phenomena. Third criterion has been the inclusion of major mountain systems capable to catch the interplay between soil moisture, integrated water vapor, rainfall, and snow feeding in a comprehensive manner, not only locally, like in the Great Alpine region in Pyrenees, but thinking also about to the downstream effects. This is an example related to a flood event that took place at the end of May 2024. It affected the northern part of the Gar region with up to 300 millimeters of rainfall in 3 days, but the propagation was downstream into the upper Rhine part and to the tributaries of the Danube complex river system with significant economical and societal impacts. Now, built on top of the area of interest, how we derived the mission requirements. We adopted an approach based on observing system simulation experiments, OSSI, very well consolidating literature, where we have a nature run representing the truth, where we can extract observation in the simulated world to apply quality control actions and tend to use those data either into a monitoring or data simulation logic, then checking the results and assessing the impact of those observations. In the case of the scientific goal number 1, I like to stress a little bit more the temporal sampling and spatial requirements. This is a result of an OSSI experiment. It is the evolution in time of the integrated water vapor content in central Mediterranean, associated rainfall depth, hourly scale. The third panel is related to the sampling from Sentinel, and you see how it is missing a lot of the temporal spatial evolution. The last panel is related to a GNSS network, which has a very good temporal coverage, but sparse density. From this evolution, it is apparent a requirement of observations of spatial scales below 10 kilometers, below convective scales, and at least 6 hours. In order to get the information for integrated water vapor content, we have performed different OSSI. I'm reporting the results for an OSSI experiment implemented in the SEM region. The red contour is representing the truth rainfall contour for an extreme event. We are above 300 millimeters in a few hours. The bluish contour is related to the atmospheric modeling without any assimilation, and you see a significant error in localization. By performing the Hydroterra Plus data assimilation, integrated water vapor content, we can correct the localization, get closer to the actual truth. And the interesting thing is that despite we know that Hydroterra Plus is blind over the sea, having the data over the land, we can still achieve a significant correction. Working with the GNSS data, the results is getting worse. The bluish color is shrinking a lot, and the take-home message is that with the Hydroterra Plus simulation, in this experiment and other reported in the RFA, it is clear that there is a positive impact. In terms of requirements, we are speaking about axis hour revisit and 2 kilometer resolution as a threshold value. Let's move to the surface soil moisture. As Harald said, surface soil moisture is a key driver for water cycle, is a key ingredient also for the societal and economical dimension, thinking about agriculture. And it is essential to know it to have a proper irrigation management and water resource management. Again, in this case, we have used a NOSI approach. We have performed a simulation with WRF Hydro, and we got an estimate of surface soil moisture. We inverted the problem using SM2Ray software to get the irrigation, and this plot is providing the synthesis of the results. We are comparing the performances versus the revisit time for 2 levels of retrieval error for a semi-arid region. And whenever we consider the user requirement from a survey performed with farmers, it is apparent that only Hydroterra is capable to achieve the user requirement value with a revisit time below, around 6 hours. So the take-home idea is that we need at least 6 hours and a retrieval error in the order of 0.08 cubic meter of a cubic meter. Snow case, we start with the snow water equivalent. This variable is again very important in the water cycle in order to get a sense of the snow melt runoff modeling and the water resource management. We have focused our attention on the Austrian Alps area. The idea was to get an estimate of the possible impact in the estimate of the snow water equivalent on hydropower production and water resource management. And what we are getting is that if we consider an uncertainty in the order of plus minus 25% in the snow water equivalent, at the end of the 4 months period in early July, we can get an error of 5 million cubic meter, which is a very big difference in terms of implications for energy production and water resource management. But snow water equivalent is not only about the only variable about snow. Very important is also the snow mass phases. And the 2 variables are producing requirements which are reported in the final table. In the case of the snow melt phases, we are here moving more into the considerations of the latent and sensible heat fluxes, and this variable is very important as boundary condition for atmospheric modeling and in general as an element for planetary boundary layer phenomena. Again, a NOSI experiment approach. We are considering a snow-covered surface of 3,000 meters in the Austrian Alps, and we are showing that depending on the sky conditions, we have very different answers in terms of snow melt. This graph is showing the time evolution of the snow melt in orange for a cloud cover condition, and you have certain values. Whenever in a NOSI logic you perform a simulated clear sky condition, you see a strong impact. Why? Because in clear sky condition, you have stronger long-way outgoing radiation. You have a change in latent and sensible heat fluxes, refreezing phenomena stronger over the night, and the melt rate is reducing significantly, almost by a factor of 2. From those OSI experiments, we are supporting a requirement for snow melt phase in the order of 6 hours as threshold value. Scientific goal number 4 is related to the deformation in the line of sight. In this case, we are moving to our attention on earthquake and volcanic phenomena. And we are aware that LEO stars have currently revisiting time which are not consistent with the temporal and spatial evolution of those phenomena. This is an evolution of the deformation associated with a volcanic eruption in the Etna volcano in Sicily, in southern Italy, every 1 hour. And this event was associated with transient deformation lasting 6 hours, okay, and with a very complex evolution with acceleration and deceleration, calling for a capability of monitoring those phenomena at very high spatial temporal scales. Moving to the goal value, in this case, we are speaking about a revisiting requirement in the order of 1 hour and a spatial resolution in the order of 50 meters. This journey has brought us to this summary table, which is covering for all the Hydroterra Plus Level 2 products the full set of mission requirements. We have the different products, and we have a distinction in terms of accuracy, spatial resolution, and temporal resolution in terms of threshold and goal. And every product is mapped on different areas of interest, which are summarized in the last column. Thank you for your attention. Now I leave the floor to Andrea Sita for the technical part.
Thank you, Antonio, and thank you for having presented this scientific requirement. So in the next section, I will bring you from the science case to the mission architecture, from what we need to how we get there. So to answer the different geophysical observation need of Hydroterra Plus, we have selected a microwave remote sensing technique to enable day and night and regardless cloud coverage observation conditions. Among all microwave remote sensing techniques, we have selected a synthetic aperture radar that can enable high spatial resolution retrieval of the geophysical information via backscatter and interferometry. Interferometric capability that is a key for our integrated water vapor, snow water equivalent, and ground motion variables. Finally, the frequency. We have selected a C-band that is the best compromise between the water content sensitivity and the resilience to ionospheric conditions. Now, the choice that shapes the whole mission architecture, the orbit choice. So, given the temporal revisit on one side and the spatial coverage on the other side, we understand that we need a highly flexible mission. That a mission that should acquire the area of interest 4 times a day, or a mission that needs to acquire a specific target 20 times a day. So our solution to these needs is a near geostationary orbit, an orbit whose period is matching Earth's rotation, the sidereal day, thus enabling large persistent coverage of large areas. Geostationary altitudes meant large slant range and low satellite-to-target relative velocity. These two parameters directly affect the noise equivalent sigma 0 performance that set the noise floor for our observation. The noise equivalent sigma 0 performance has been a key focus for our phase 0, where we had a very important trade-off between the antenna diameter on one side and the transmit power on the other side. Finally, the low relative velocity, together with the spatial resolution, also means a very long integration time. Hydroterra Plus integration time baseline is 1 hour. With these system drivers in mind, during phase 0, we have elaborated 2 system concepts proposed by 2 different industrial teams, led by Airbus Defence and Space Germany as System and Platform Prime, and Airbus UK as payload prime on one side, and OHB as both system and payload prime on the other side. Now, let's have a look to the overall mission architecture. The space segment is composed by a C-band synthetic aperture radar satellite operating in spotlight mode. The satellite configuration is strongly driven by the selection of the reflector, as we will see more in detail later. The benefit of being in geostationary orbit is allowing us to have continuous visibility towards the ground. That's enabling the capability of having a dedicated ground segment, including continuous payload data acquisition through X-band, while flight operations, so telemetry and telecommand, are performed through links in S-band for concept A and X-band for concept B. Finally, the launch vehicle selection, Ariane 64 in dual launch configuration, is our baseline. So we said geostationary orbit, but how do we get there? During phase 0, we have evaluated VGC to be unsuitable for Hydroterra Plus. Indeed, the very low altitude insertion implies a long transfer to the geo-orbit with electrical propulsion that exposed satellite equipment to a very severe radiation environment, making the system very complex and thus unfeasible. Ariane 64 launch to geostationary transfer orbit in a dual launch configuration is therefore our baseline. We can see that both concepts fit in the smaller dual launch structure in both position, upper and lower position. Ariane 64 will inject Hydroterra Plus in the blue orbit, the geostationary transfer orbit. Then several apogee maneuvers with the chemical apogee engine will raise step by step the perigee altitude till we will reach the target geostationary altitude, where a final set of maneuvers will allow to fine-tuning the orbital parameters we need for Hydroterra Plus mission. So now we are in GEO. The GEO orbit is governed by the International Telecommunication Union regulation, and for an experimental stations like a future Earth Explorer 12 will be, the maximum east-west elongation is plus minus 0.5 degrees. This is directly driving the maximum eccentricity of our orbit. For what concerns the inclination, the need for subdaily interferometric acquisition means that we need the reference target to be in the same orbital plane as the satellite, the zero baseline orbit condition. Now, with this orbit in mind, in pink in the figure, we can see the ground track of the orbit projected onto the Earth's surface in an Earth-fixed reference frame. We can see that the ground track is an ellipse in almost perfect quadrature with latitude and longitude, with longitude driven by the maximum east-west elongation of the eccentricity, and latitude driven by the inclination. This ellipse has been divided into 24 one-hour slots, thus matching our integration time. The observation concept of Hydroterra Plus is designed around the spotlight SAR observation mode. In spotlight, the antenna beam is kept fixed over one point during the whole integration time with the mechanical steering provided by the platform. Mechanical steering that is also allowing to move from one target to another. We have defined two concepts of operations. The first one is the regional campaign. The regional campaign answers to the need of observing one area of interest with a temporal revisit of 6 hours. So during the regional campaign, we will focus to one area of interest at the time. In this example, we will focus on the Greater Alpine region. The orbit has been further divided into 4 different regional campaign slots, the brown arcs in the figure. And when the satellite is entering into this brown arc, it will acquire the full area of interest with 4 different footprints. The regional campaign runs systematically every day, thus enabling interferometric capability with the temporal baseline of 24 hours. We can see here that we also have 2 2-hour blue slots around the apogee and the perigee of the orbit. These slots have been called the taskable slots and allow Hydroterra Plus to be a highly flexible mission, because in the taskable slots we can look outside the area of interest that is the focus of this specific regional campaign. And the taskable slots are also enabling interferometric capabilities with the sub-daily temporal baseline. Now, the regional campaign runs systematically over one area of interest for about 1 year. Then, according to mission phase definition, we will progressively cover all of them. In this picture, you can see how all area of interest can be observed with 4 different footprints. Now, the second concept of operation, the steering campaign. In this concept of operation, we are leveraging the capability of Hydroterra Plus to achieve a temporal revisit down to 1 hour over one specific target. For example, we can look to Vulcanos in Sicily, south of Italy, in this figure. During the steering campaign, the full campaign slots, the brown arc in the figure, are reserved to that specific target, the footprint number 1, leading to up to 16 acquisitions over it and 8 interferometric couples. The taskable slots can be still kept for having more flexibility, or we can use the taskable slots to again observe the same target, leading to up to 20 acquisitions of it per day and 10 interferometric couples. Now, the quality of interferometric products is strongly driven by the capability of the satellite to repeat the same observation geometry. This capability is governed by the normal baseline. Taking 2 different spacecraft positions when we are acquired the same target, the normal baseline is defined as the normal component of the relative spacecraft positions projected onto the plane containing the line of sight of the reference acquisition and the ground normal, the surface normal. Now, both concepts have defined a station-keeping strategies that will allow to maintain this normal baseline well below the requirement, that is 4 kilometers. The normal baseline has been evaluated over a 7-day sliding windows. This allowing to smooth both short-term fluctuation and also tracking orbit control compliance over time. Now, the satellite configuration that have been proposed, here we can see concept A and concept B. Concept A is being based around a deployable petal reflector, 5 meters, mounted on top of the nadir panel, while concept B is based on a large deployable reflector, the Simmer one, 7.1 meters, mounted on a boom on a lateral panel of the satellite. While both concept relies on elements from MTG platform, especially for adaptation of the structure and the same chemical propulsion. Then concept A is based on Astrobus Neo building block for avionics and equipments, while concept B is leveraging the capability of MTG to be adapted for Hydroterra Plus needs. Now, briefly, the satellite budgets. We can see that the mass budget is fitting with margins with the launch mass capacity, half of an Ariane 64 to GTO performance. For the Delta V budget, both concepts are enabling a 7 years extended lifetime. And we can see here that the main contributor to the Delta V budget is the GTO to GEO transfer. Finally, the power budget. In the second slide, I said that the key trade-off was between antenna diameter and transmit power. Here we can clearly see the impact of the different reflector choices. A transmit power for the payload concept A, 3.2 kilowatt, and 1.6 for concept B. Now I hand over to Valeria, the payload manager, to present in more detail the payload architecture and the satellite performances.
Thank you, Andrea. Okay, so Andrea mentioned that the noise equivalent sigma 0 is the main performance parameter for the payload design, and therefore on this slide I would like to talk about it in more detail, and I'm sorry I have to show a few equations for that. So the noise equivalent sigma 0, what is it? It's basically the noise floor of the signal-to-noise ratio. In order to have the signal-to-noise ratio as high as possible, we want to keep the noise equivalent sigma 0 as low as possible. Here you see that the noise equivalent sigma 0 depends on several orbit parameters. The slant range, which is the distance between the satellite and the target, and the satellite velocity. Here I have put some rough average values of Sentinel-1, which is a SAR mission in the LEO orbit, and of Hydroterra Plus, which would be a SAR mission in the GEO orbit. And you see that the slant range for Sentinel-1 is 900 kilometers, while for Hydroterra Plus, it would be 37,000 kilometers. And this, of course, has a huge impact on the noise equivalent sigma 0, because, as you can see, it's to the power of 3. It's true that also the satellite velocity is slower for Hydroterra Plus, which is favorable for the noise equivalent sigma 0. But still, the difference between LEO and GEO is 24 dB. So plus here means bad. That's why it's red. And then the question is, okay, what can we do about this? In blue, you see the instrument parameters. And you see that the noise equivalent sigma 0 depends on the average transmit power and the two-way antenna gain. So we would like to have the average transmit power as high as possible and also the antenna gain as high as possible. In order to have the average transmit power as high as possible, we need a high power amplifier, which amplifies the transmit signal as much as possible. And to have a high antenna gain, we need to have an antenna which is as big as possible. So, okay, Hydroterra Plus is a mission which has to transmit with a lot of power and which has to have a big antenna. But of course we are bounded by the available technology for this, so we need to have a look that we can choose something that is credible. Another important parameter is the instrument bandwidth. The smaller the bandwidth, the better for the noise equivalent sigma 0, but also the single look range resolution is impacted by the bandwidth. So the smaller we choose the bandwidth, the better for the noise equivalent sigma 0, but the worse for the single look range resolution. And this is an important trade-off that we have to do, and I will talk about it in more detail later. You see that also the azimuth single look resolution is impacted by the orbit parameters, specifically by the slow satellite velocity. But an important parameter which can be chosen for the azimuth velocity is the integration time. The integration time is the time during which a SAR image is formed. And you see also here the big difference between LEO and GEO. For LEO, this parameter is fixed. So for certain technology, it cannot be changed, while for GEO, it's a freely selectable parameter. And for Sentinel-1, for the SAR image focusing, it's less than 1 second, while, as Andrea mentioned, for Hydroterra Plus, the baseline would be integration time of 1 hour. And of course, this also has significant implications, about which I will talk about later. Yes, here you see the overview of the payload concept of Hydroterra Plus. So, okay, it's a radar. So just very shortly, how does a radar work? We want to transmit a signal, so the signal is generated. Normally we generate chirps here in the frequency domain, then it's transferred to the made analog and upconverted to C-band, which is 5.4 gigahertz. Then the signal is amplified, it's transmitted to Earth to measure the great science products. Then it's received, and on the receive chain we have basically the same procedure. We amplify the signal, we make it digital and transform it to baseband, and then we save it as science data. So now I'd like to talk more about the differences between concept A and concept B. So here this part of the radar is called backend, and for concept A, the baseline is to use the universal processing module, which of course benefits highly from the heritage with Roselle. Here you see some up-to-date picture where it's being tested. And for concept B, the baseline is to use a new development from Antwerp Space, or as a backup also the backend from which was developed for Harmony is considered. On the next slides, I would like to focus on the antenna and the high power amplifier block, because as discussed on the slide before, these are basically the key technologies in order to meet Hydroterra Plus requirements. Here you see the antennas for Hydroterra Plus, for concept A and concept B. So for concept A and concept B, there are 3 antennas which can be used in order to achieve all Hydroterra Plus requirements. I would also like to mention, okay, they are all deployable reflector antennas, but the technology is actually quite different. So you see for the baseline antenna of concept A, the reflector consists of 36 petals, which are solid panels, which are then basically folded to store the antenna. And for the baseline antenna of concept B, the reflector is made of a mesh, which is a very fine material. And as was mentioned also by Andrea, the sizes of these antennas are quite different. So yes, basically the main point that I would like to make for Hydroterra Plus, 6 different antennas can be used, which have more or less different technologies and from 4 different suppliers. So I think on this, with this technology, we are quite on the safe side. In this slide, I would like to further talk about the high power amplifier block. Here you see the architecture of the high power block for concept A and concept B. The difference is that for concept A, 2 amplifiers are used, which are then combined with a switch in order to increase the average transmit power. And for concept B, only 1 high amplifier is needed. Why is this? It's because, okay, we are having a smaller antenna for concept A, so we need to transmit more power. As I was showing in the noise equivalent sigma 0, it's a product. Basically, the higher the power, the smaller the antenna has to be, and vice versa. An important point is that both consortia have chosen the traveling wave tube amplifier. The traveling wave tube amplifier needs an electronic power conditioner. It's basically to transform the low voltage of the satellite to the high voltage which is needed by the traveling wave tube. And yes, for Hydroterra Plus, they have to be developed. So these are new developments for Hydroterra Plus, where the driving requirements is the high output power, okay, as you can guess, the long pulse length, and also the continuous operation. But I think it's important to say that both consortia, they have agreed on the same set of requirements, so we could, so to say, join forces here. And we have done 2 risk retirement activities, 2 risk retirement activities on the traveling wave tube, and also 2 risk retirement activities on the electronic power conditioner each. With the same set of requirements. And I think it's also important to say that the suppliers do not start from scratch. Here you see some, basically you see the heritage that they have, which then have to be adjusted for Hydroterra Plus. And okay, I think it's also important to say that the suppliers did not identify any showstoppers, which is good. On this slide, I would like to talk about the 2 main level 1 performance parameters for the products. So as was already mentioned, what's needed for the science is are the interferometric products, which is basically the phase difference between 2 SAR images, and backscatter products, which is the amplitude, or the geophysical targets are then derived from the amplitude of the SAR image. And the interferometric product is impacted by the interferometric phase noise, and the backscatter product is impacted by the radiometric resolution. The other Andrea will talk more in detail about this. So just very shortly, what I wanted to say is that all the requirements or parameters that we have talked about, so the noise equivalent sigma 0, but also the orbit requirements, they can be flown down to these 2 parameters. And also another important point that I would like to make is that we know that due to the long integration time, there are additional contributors that have to be considered. And we've actually spent quite a big effort in the system studies, but also in the SAREC, the science activity, and with the MAC members to model these contributors, and they are included in these performance parameters. Yes. So this is my final slide. Here you see the computed parameters for concept A and concept B for the 3 primary science goals. And I think what's important to say here is maybe you remember that the bandwidth has to be can be optimized, and concept A has chosen the bandwidth to be compliant to the noise equivalent sigma zero requirement with 1 dB margin. And you can see here that the single look resolution, there's actually still quite a lot of margin as compared to the requirements that we have. While concept B has chosen the bandwidth in order to be compliant to the single look resolution requirement, and you can see here that there's actually still quite a lot of margin for the noise equivalent sigma zero. So we have some room to optimize the parameters. Another important thing that I think is important to mention, that you see here for the radiometric resolution and interferometric phase noise, we also have quite a lot of margin between the requirements and the values which were computed. So they can also be, yes, we can also use this margin in case we need some further adjustments. And of course, the main point is that we are compliant to all threshold requirements with both concepts and for all science goals. Yes. Then I would like to hand over to Tim Wright, who will talk further about the processing of the level 2.
Thank you, Valeria. So Hydroterra Plus is a product generating system, not just an imaging mission. From the same radar observables, we're able to create products that span the land surface, the atmosphere, mountain cryosphere, and hazards. I'm going to talk about how we go from those raw radar returns through to those level 2 products. We've already heard a bit from Valeria about going from the raw data through this long integration time. And essentially that leads us to these 2 routes, one via backscatter and one via phase. If you want to think about backscatter, that's the strength of the image coming back, and the phase is related to the path length. The backscatter is related to the surface state, and the phase change, again, related to the path length changes. Before we can generate those products, for each of the amplitude-based products and the phase-based products, there are some pre-processing stages that we need to go through. In both cases, some calibration, some multi-look averaging, and some projection to geographic coordinates. For the case of the interferometric products, we also need to compensate for some using some prior information on topography and things like that. It's important to stress that the amplitude-based products can be derived from single images, whereas the interferometric phase products basically derive from differences between images and or stacks of images. So I'm going to go through these products one by one and really give a very, very high-level description of the retrieval algorithms. Starting with the backscatter-based products. So we've known for a long time that surface soil moisture is essentially correlated with radar backscatter. This is a figure from Ulebi et al. In 1978. And essentially that methodology is now operational. This is the Copernicus Land Monitoring Service daily surface soil moisture product. Although, of course, it's a daily product. If you look at any one point with Sentinel-1, you don't get an image every day, and you certainly don't get the sub-daily images that we'll have with Sentinel-1. The snow melt phase, the discrimination of snow versus wet snow versus refrozen snow is basically based on temporal backscatter changes. You can see from this nice data from the HydroSui campaign that there's really quite strong differences in backscatter between dry snow and wet snow. Here you've got dry snow at the start of this time series, and you can see in this period we've gone through various melting and refreezing stages. And the changes here are much, much bigger than 5 dB, so very, very straightforward to detect with our system. And from that, you can then create these maps. Essentially, it's a classification problem. You can see here for 2 different days in 2019. On the 20th, you've got this distribution of wet snow and dry snow. And then on the night of the 21st of April 2019, some of that wet snow refroze. So you can get very detailed information about how snow changes its state. The phase contributions are a little bit more complicated, and it's worth stating that the phase contains multiple contributions that we need to separate. So those include the geophysical signals that we're interested in this case, but also some terms that are related to, that are essentially noise for our products. We can look at an interferogram and just illustrate some of those terms systematically. This is for Sicily, and you can see this is an interferogram from Sentinel-1. It's a 12-day difference in the phase between images acquired on the 16th and the 28th of December in 2018. And you can see multiple contributions in this image. So if we look here, we've got these incredibly beautiful kind of herringbone pattern of atmospheric gravity waves. And you can see the detail that you can get from an interferometric product in the state of the atmospheric water vapor there. Very, very detailed information. The other beautiful signal in this image is Mount Etna. And in this period, there was an eruption and a volcanic intrusion that you also see very nicely in this image. We can also see some areas of noise, so there's a little bit of disturbance in the phase. We think in this particular case that's a north-facing slope, likely to be perhaps some wet snow or some vegetation there, causing a loss of signal. And it's important to stress that there's more than 30 years of research now in SAR interferometry in academia and in industry that have developed robust operational methods for separating these signals. The noise terms I'll go through one by one. There's a topographic term that can be removed essentially using an a priori digital elevation model, but you can also solve for it based on the signals in the data. There's some long wavelength signals that come from features like the atmosphere, like the ionosphere. These can be removed either with a priori models or through calibration with ground control data. We've heard about noise equivalent sigma 0 from the previous speakers. This is system noise, white noise that affects each pixel in our observations. And there's also this term that comes from the intrinsic target phase, and that's where the targets are moving around, and that's essentially, it gives us a loss in coherence. And I note that one of our secondary products has a change maps that actually exploits those changes to make maps of features like lava flows or floods. Complex multi-looking reduces the contributions from loss in coherence and system noise, as previously described. In terms of the geophysical signals that we're interested in, there's relatively simple retrievals for all of these. For the integrated water vapor, that's essentially proportional to the phase term, and we know the terms in this constant of proportionality here. So we can invert for IWV on each epoch in the time series relative to a reference. Same is true for the snow water equivalent. Again, we know these terms in the constant of proportionality very well, or they can be measured in the field. And so we can do that inversion for those changes in snow water equivalent. The non-triangular phase is a little bit harder to get your head around, but essentially what that is if we look at 3 consecutive images and form these interferograms as shown in this little schematic here, and look at the differences, if there's no changes in things like soil moisture, that should be 0. And if there are changes, if it's non-zero, then that is related to the soil moisture. And this is one of our experimental products. Deformation is simply linearly proportional to the change in the path length. So again, a relatively straightforward retrieval. Of course, the challenge is that all of those terms are present in one signal. So it's how do we separate those? And fundamentally, we do that based on their temporal and spatial characteristics. The integrated water vapor is correlated in space, but impacts each individual acquisition epoch differently. The deformation is also correlated in space for features like volcanoes, but impacts all interferograms spanning the time of movement. The non-triangular phase can be calculated from these loops. And snow water equivalent, there we use reference stations based on higher local meteorological sites to calibrate the phase change due to snow accumulation. I want to stress that there's a huge level of maturity here in the literature, going back to the 1970s for many of these forward models, going us all the way through validation, all the way through to operational products for surface soil moisture and deformation that are part of the Copernicus system using Sentinel-1 data. Of course, not with the frequency of updates that are going to be possible with Hydroterra Plus. Finally, there's an extensive set of user communities ready to exploit these data, both in meteorological community, hydrology, the snow cryosphere communities, and the hazard communities. These range from national organizations like Meteo France through to regional organizations in Europe like ECMWF and in Africa, and also wider organizations, global organizations like the World Meteorological organization. And with that, I'm going to hand over to Andrea Monticorneri, who's going to talk more about the scientific feasibility of generating these products. Thank you.
Okay, thank you, Tim. And now we discuss about the feasibility of Hydroterra Plus product. And they have all been generated either by the estimate of the backscatter or the estimate of the phase. And the core of the estimate is a multi-look average. So what really drives the sensitivity is the number of look, which is a ratio between the level 2 and the level 1 resolution area, noise and coherence. As a number of look, a reasonable number to detect different values of backscatter and coherence is starting from 5, but you would like to have 10 or more. That is why you set a threshold resolution for the level 1 by taking this number of look, accounting for some noise, and considering the finest resolution product, level 2 product. So this both requirement has been shown feasible. And now we come to the sensitivity of surface soil moisture that has been computed by a Monte Carlo simulation basing on the radiative transfer zero-order model that was used for Sentinel retrieval, the Copernicus product. And we get to result when you go to Hydroterra frame that with noise equivalent sigma naught worse than minus 18 dB, we cannot get a reliable estimate, and that's been set as a requirement that is feasible. And then you see in the performance plot that with less than 50 looks, 20 looks, performance drops. So you really need to apply for a significant number of looks that you get with the threshold resolution of 1 kilometer. That is the one of the present Copernicus product. And in this case, you have enough look to perform better than goal, even considering a medium vegetation coverage. As for snowmelt phases, this is a product in which you have discriminate between wet and not wet, and you do it by considering a threshold at least 3 dB in backscatter. And for the thresholds, the performance models, now performance is error probability. You can get it with the 500 resolution, and you see the error probability is here again better than threshold, than goal. And here we are. Now we start with the interferometry product in which coherence is really the essential driver for the quality of the interferometry product. Coherence is the similarity between two acquisitions of the same target in different times. And in Hydroterra Plus, we have 4 factors. The volumetric component depends on the repeatability of the orbit. So recent literature shows that a good compromise between orbit control and coherence could be a baseline of 4 kilometers that has been set as a mission requirement. But as you see, the mission performance is much better than this requirement. As for the temporal decorrelation, that is the most important because you can do anything for that. You see on the left, you see Sentinel temporal decorrelation that you get when you combine one Sentinel 1C and one Sentinel 1D image that is a 6 days revisit. And you see that the coherence is pretty good over the desert areas, is even more than 0.7. But when you go to the vegetated areas, here in summer, that is worst case, you see coherence is blue. Blue is pretty bad because it's less than 0.2. However, when you go to Hydroterra and you look at the temporal decorrelation in 1 day revisit, things totally change because in the desert area you are not so good because the Hydroterra signal to noise is several dB worse than Sentinel, and it has also the atmospheric decorrelation on the top of it. But if you consider the vegetated areas, now the 1 day revisit overcompensates the correlation, and you have a figure that is much better than Sentinel, and the good news for interferometric product. So for the EWW, you compute the accuracy by taking the standard deviation of the phase, you propagate to the EWW relation by the linear relation, and then you have also to account for the fact that interferometry is always a differential measure. So in order to make absolute, there are methods in literature. You have to consider more than 2 images, to take a stack, and in the stack you should consider a global atmospheric model to make it as a reference. Then if you compute the performance, you see by using the 1 kilometer resolution, that is the goal, you have that sensitivity. And you see the worst case is 0.2, but in many cases you are even less than 0.1 kilogram per square meter, and the requirement is 1 kilogram per square meter. So you are many times better than the goal. And you can spend this margin, for example, for having alpha resolution, or you can spend it for doubling the coverage, because when you are in a steering orbit, you can decide what is a compromise between resolution, coverage, and sensitivity as you will. For the snow water equivalent, it's the same story. So you take the accuracy of the phase, you introduce also the uncertainty of the reference, and in the end, you see the performance by using the 500-meter resolution, and here again you see the performance in terms of sensitivity is much better than goal. And if you look on the top right plot, you see this comes from Sodankila campaign. You see all over the winter and up to March no accumulation, and all the top graph, it's what you expect by using the in-situ information, the scale, there's no scale, but also by using the 24 hours or the 12 hours interferometric revisit. And the orange plot show what happens with the 6 days, that is a coherence constellation revisit, interferometric revisit. So you see Sentinel is not able at all to get this product, and that is why this product is not really produced now. So as for validation of this concept, we base on 4 pillars. Tim has already described the literature that is widespread. I can add also that there is a consistent literature of geosynchronous system, starting from the very first paper in 1978 by Kyoto Miyazio. And for the scientific performance simulator, we provided code for every product, considering also the secondary product. And I can say that all these products are feasible within the requirement. You see, for example, a verification of the sensitivity of the EWW product on the right. On the middle, you see 2 histograms superposed that shows what happens if you degrade the noise equivalent sigma naught of 1 dB on the performance of soil moisture estimate. And this is why we derive the minus 18 dB requirement that drives basically the design. And on the left, this is another interesting point, because when you see Europe from the equator, then incidence angle becomes very high, and you wonder how is the visibility of the slopes, particular at high latitude and particular in rugged topography. So I consider Alps as a worst case, and you see this is a visibility index. Blue is perfect visibility. 0 is total no visibility at all. So you see nothing is really perfect. Of course, we have a problem with shadowing, much major problem, but in the average, the visibility is much better than what I personally expected. And for campaign, you see, we started campaign with Hydroterra missions that has been a candidate Earth Explorer 10, and this campaign was very useful because we had the opportunity to get the data, to analyze them, to do a statistic evaluation, to refine algorithms. We find out what happens, for example, for soil moisture under a vegetation coverage or at a high incidence angle. We have a good result about the correlation. We have a good result for for SWE. And you don't see a campaign on atmosphere, and that is because atmosphere is ubiquitous. So whenever you do a campaign or a SAR observation, you do have the atmosphere, and you have to cope for that. So finally, we have compiled a risk assessment for all the product and for all the mission objectives. And I just gather it here, what are the most relevant, so that medium risk, and you see that there are risks affecting the overall interferometric product, as well as some risk on soil moisture or on vegetation and SWI. And for this risk, and we have planned some campaign, but we also have put some mitigation strategies in the roadmap. So I thank you for your attention, and I would like to invite my colleague Vasiliki Kotroni, who will discuss about synergies and complementaries.
So, dear participants, what if we could observe the water cycle at the time scale it happens, that is in hours? Hydroterra Plus is particularly timely. Why this? Because key water-related processes happen in hours or minutes and are not fully observed by current observational capacity. Secondly, because extreme weather events, it has been already discussed, have becoming more intense, and also the water cycle is becoming more disruptive. And this is the reason why we need better observation to better understand and better forecast water cycle-related events. And thirdly, the technological window. Geostationary SAR now is technically achievable, and phase 0 has confirmed that there are two valid industrial concepts. So Hydroterra Plus is not competing with existing missions, but it should be considered as a multiplier of them. Let's start with atmospheric processes and integrated water vapor. Sentinel provides the fine integrated water vapor snapshots, but not the sub-daily cycle, because there is a revisit of 1 to 2 days. Passive microwave products provide the large-scale moisture background, but at a coarser resolution. GNSS networks provide high temporal information, but only at station locations. And it is Hydroterra Plus with a sub-daily kilometer-scale integrated water vapor fields that will provide the missing observational scales, will extend the moisture monitoring beyond the limits of ground infrastructure, and will support multi-sensor integrated water vapor products, and also improve retrieval validation, and also the use in assimilation and forecasting systems. Furthermore, there is a synergy with winds in clouds and precipitation that will be measured by the Wyvern, which, along with thermodynamics moisture provided by Hydroterra Plus, will help us unlock the full picture of convective initiation. Let's go to terrestrial water cycle and then surface soil moisture. Sentinel, NISAR, Rosel provide the spatial detail, SMO, SASCAT, SIMMER, the core scale context, but is the sub-daily kilometer scale surface soil moisture fields that will be provided by Hydroterra Plus that help enhance the temporal information content of Copernicus Land Monitoring Service, remove signal aliasing, and provide seamless course to find surface soil moisture chain. Moreover, there is a synergy with local in situ networks like the cosmic ray neutron sensing in the Volta region, highlighted in the beginning of the presentation by Harald, and also the international soil moisture network that provide ground truth information and will help validate Hydroterra Plus. Let's go to the third pillar, cryospheric water cycle. Here, LEOSAR provides the fine spatial snow water equivalent, but at multi-day repeat intervals. SIMMER and AMSTER 3, the core scale context over suitable terrain, but it is the sub-daily, sub-kilometer scale, snow water equivalent, and snow melt phase provided by Hydroterra Plus that will help us have and obtain a gap-free, basin-wide snow budget and information about the diurnal melt-freeze evolution, will support snowpack modeling, and also provide all critical information which is needed for hydropower, reservoir management, and flood season forecasting. Last but not least, about ground motion surface and surface change, LEO INSAR provide the fine spatial resolution, but the revisit time may miss fast movements. And it's the sub-daily kilometer scale deformation by Hydroterra Plus that will help unwrap LEO phase for fast evolving events, while with the almost north-south geostationary line of sight will help us complete the 3D decomposition of the formation. Furthermore, there is a synergy with the new constellation of commercial small stars, which in their turn observe with high temporal sampling, but with small footprints when tasked, while Hydroterra Plus will provide the broad view, the large view, and support early warning detection for later tasked LEO acquisitions. So summarizing, compared to LEO-SAR, Hydroterra Plus will provide the diurnal cycle resolution and enable us to have a causal process attribution of the events. Moreover, we will be able to observe the build-up of the events and not just their aftermath. We will have a multi-domain and instrument consistency because we will have 6 geophysical parameters that will be acquired simultaneously. So this will provide a coherent view of processes along the atmosphere, the land surface, the cryosphere, and the hazard domains. Furthermore, we will have an interferometric advantage that will unlock applications that require more frequent insert. And last but not least, compared to GEO, we will complement optical and thermal infrared GEO sensors because we will provide the all-weather day and night active microwave capability. So here are our key takeaway messages. The gap is real and urgent because there is no observing system, current, or plant that observe the combined spatial and temporal scale and resolution and all-weather microwave sensitivity needed to observe the fast water cycle processes. Hydroterra Plus is unique because it will be the first GeoSARth Earth Explorer mission and concept that will provide regional, sub-daily, sub-kilometer sampling of 6 geophysical products simultaneously, and there is no other mission that is doing that. Hydroterra Plus is amplified through complementarity with the other missions, and the other missions will also gain scientific utility by this complementarity, while Hydroterra Plus it's the only one that will provide the temporal link at kilometer scale across all 4 science domains. Finally, phase A is timely. Hydroterra Plus is a timely mission because the technology is there now. The observational niche is unoccupied, as it has been shown, and Hydroterra Plus gives ESA and will give ESA and the scientific community the first taskable radar, Earth Observatory in GEO, that will be able of observing the pulse of the water cycle at the pace it beats. Thank you so much. I thank you for all.
I have to say I'm always impressed by the presentations at the UCM, and I would like to thank the team, the MAG, the presenters in particular, for this excellent job. So it is now up to me and to my colleague Bernardo Carinciero to do a bit of the housekeeping that we're doing to look into the programmatics. So we'll try to keep this short. It's just giving you basically also the view on our side on how we see the progress on what we see on the programmatic side, where we stand. We'll try to make this relatively brief, and I can promise you my presentations will be amongst the most boring ones that you have seen on stage, and this is good like this. So we're first coming to the scientific maturity. And here, considering the activities that Hydroterra has gone through in phase 0, and also, of course, what has been documented in the reports for mission assessment and the nice presentation that we've just seen, the MAC, the campaign and the study teams have clearly established the scientific goals and also shown the full traceability to the objectives and the requirements. They've provided also an adequate and independent review of the model, or there is one, which is allowing the computation of measurement data based on the geophysical input data. We have seen this as well very nicely. They also produced a demonstration data set using realistic geophysical and input conditions. They've demonstrated the sensitivity to required observations, so to target geophysical parameters using campaign data and numerical modeling simulations of the observations, and also provided preliminary retrievals, including also an information content analysis. They assessed the scientific concept against the complementary and alternative missions, what we have also seen just now. And they have identified also scientific risks and associated mitigation activities. And one thing which has also been important, we have started development of the end-to-end simulators, which is also helping us with the geophysical assessment, and also here the geophysical scenes have been identified. So overall, on the basis of what has been presented, on the basis of what has been provided also in the reports, we consider that the candidate mission team has demonstrated what we call the scientific mission concept feasibility. And with this, it's basically shown that the mission is at a scientific readiness level of 4. So this is the first element. So here we're confirming that we see that SRL4 has been achieved. Another element is, of course, the assessment of the risks that are there. And we have seen that also here the MAC, the campaign, the MACs together with the campaigns and also the study teams, they have been looking into the risk and also the mitigation activities. And overall, it is considered that on the scientific side, it carries a low scientific risk that what has been provided here would not be able to be accomplished. So they have shown that the evolving system observation capabilities and strategies are an element to look in the integration of the established external model data sets and complementary observations and the availability of data from ongoing and future campaigns. So these are elements that they have identified, but of course, this is answered to by a scientific roadmap, which the teams have been providing as well. And within the scientific roadmap, which we consider to be credible, they have highlighted that further OSIs for integrated water vapor assimilation towards longer periods and corrective scale refinements and observation operators and data assimilation models will be developed in the next phase. The development of adaptive calibration approaches, accounting for what we've also shown before, for vegetation and surface variability is an element which will be further investigated should the mission be selected. The assessment of snow water equivalent and SMP performance across different snow conditions is another element which they will advance in order to go towards the SRL5, which is required after phase A, as I've presented this morning. Investigation of soil moisture retrievals and the calibration. And then also OSI's observation system simulators, experiments based on the end-to-end simulator to assess the observation of rapidly evolving geophysical hazards, as it has been also pointed out, and of course then the deformation processes which are coming along this. So overall, we consider that with the phase 0 activities that have been done, the objective to mature the mission science to proceed in phase A has been achieved at this point. So from the science side, we can give a green light for going forward into the phase A. Of course, this is the programmatic assessment. This is from our side, your assessment, but in particular the one from Aceo will be then, of course, driving also the selection process. And with this, I will hand over to my colleague, Bernardo.
Thank you, Torsten. Good morning, everybody. I'm going to provide you an overview of the technical part of the programmatics, starting with some outcomes of the phase 0. And as you've seen during the presentation, the technical presentation by my colleagues Andrea and Valeria, during the phase 0 preparatory activities, each consortium has defined system concept with the capability of fulfilling Hydroterra Plus mission objectives and requirements. And another important element is that also, as you've seen, the phase 0 has defined and identified the main technical risks and critical elements for which, as explained also during the technical part, risk retirement activities have been initiated already during the phase 0, and a technology pre-development plan in order to retire these risks and increase the TRL up to 5 at the end of phase 1 has been also put in place. Regarding the heritage, critical areas and risks, and I think it's important that I mention when we are talking about critical areas, we refer to items with low TRL, but also of areas or items that are crucial for the performance achievement of the mission, but sometimes not necessary at a low technology readiness level. At satellite system, also explained during the technical part, both concepts at platform level leverage on the MTG heritage. Concept A basically reuses the structure and the propulsion subsystems of the MTG while using their own product line, while concept B is a little bit the opposite, uses the MTG product line, and it requires some adaptations in the structure and thermal to the accommodation of the antenna, and also the additional power production and dissipation with respect to MTG. Both concepts uses the MTG Liquid Apogee propulsion subsystem to go from GTO to operational orbit. And due to the change of the environment, additional environment and geo-environment, there may be a requalification of equipment and other areas and other subsystems, particularly on concept A. None of these adaptations are considered to introduce significant technical risk at this stage, but it's important to mention the adaptations that we are seeing. Point-in performance is a key requirement for the fulfillment of the mission objectives, and therefore point-in performance will remain phase A focus. Hydroterra Plus, also clearly explained in the technical presentation, fits within Ariane 64 mass and fairing envelope in a dual launch configuration, and it fits in either the upper or the lower envelope for a launch to GTO, and also it fits with enough mass and volume margins to accommodate potential design evolutions during later phases. At payload level, critical areas, or important areas identified are the reflectors, the high power amplifiers, the data processing, and for consortium B, the backend. In terms of heritage, Hydroterra Plus payload technology benefits from the longest standing heritage in Europe and Canada on X and C-band SARs. Reflectors, we have two baseline concepts. One is the large deployable reflector with heritage on the CMAR large deployable reflector, which is undergoing a qualification. And for the center-fed reflector, it builds on antennas on the same side with flight heritage on commercial missions on X-band, which for which the feed will need to be, of course, adapted. Although X-band heritage exists for high-power amplifiers, no current traveling wave tube amplifiers or electronic power conditioner fully meet the Hydroterra Plus need when we combine the operation frequency, the high power output, the continuous operation, and the long pulse duration. Therefore, basically new developments on these high power amplifier chains are needed. And for the back end, as I mentioned, for concept B is considered a new development due to the no specific flight heritage of the proposed concept. And for Consortium A, it is based on the Universal Processor Unit central unit, which is under development on Rossell for L-band that it will need to be adapted to C-band. Based on these areas, a technology pre-development plan for the phase AV1 has been put through, which focuses on, as I mentioned, the first and the most important elements, which are the TWT and the EPC, to increase the TRL and the maturity of the whole high-power amplifier chain. And for concept B, also on increasing the TRL of the backend electronics. As also other second priority, but also put in the pre-development plan, reflector backup concept on large deployment and rapid rip antennas, not only from Boxer phase, also from Thales, Italy. And for, that's going to be difficult to pronounce, back-end backup concept for phase B. And depending on the peak and average power of operations on C-band high-power RF amplifiers. Overall, it is considered that the proposed phase AV1 technology pre-development plan is suitable to retard the risk and increase the TRL to 5 at the end of phase V1. Moving on into the development approach, both consortiums will follow standard phase V2 CD1 development with parallel development on the instrument, reflector, platform, and satellite to maximize the schedule. At platform and satellite level, both concepts are based on a direct PFM approach without a structural or structural thermal model at platform level, which it is considered that it may induce some technical or programmatic risk if there are issues emerging during the PFM qualification. At payload level, I will focus more on that. For the backend electronics, concept B follows a standard engineering model, engineering qualification model and flight model, while concept A is proposing an engineering qualification model and proto-flight model. And for the reflector, concept B follow a flight model, concept A PFM philosophy. For the HPA, high power amplifier, for both concepts, a standard EM, EQM, FM approach is proposed. Finally, regarding the schedule and other programmatic considerations, Hydroterra Plus schedule is, as all these missions, basically, by the instrument development, and with the current assumptions on the start of the phase V1 and the phase V2 CD-U1, the launch in the 2036-2037 timeframe is considered achievable. Other programmatic considerations, Hydroterra Plus technical baselines adhere to the relevant ECSS standards for the Earth Explorer program. It is compliant with the current applicable space debris regulations, and there are no known ITU, International Telecommunication Union regulatory issues identified at this stage. So as a conclusion, from the technical part, no technical mission showstoppers have been identified during the phase 0 for the Hydroterra Plus Earth Explorer 12 mission candidate to proceed to phase A. So from that technical ground, no showstoppers to go to phase A. And with this concludes my presentation, almost with one, which is a very important slide, because as Christian Rossi, the mission scientist of Hydroterra Plus, more than 100 people has been working on this mission during the last about 2 years since the call was issued. And I would like to thank everybody, starting first with the MAC, following also for the science team that has been supporting all the science work that you've seen, and also all the discussions on the refinement of the requirements and the mission objectives. Our industrial teams in all the member states, the industrial teams also that are involved in the end-to-end performance simulator, my colleagues at ESA, and of course, all of you for coming here and supporting and participating in this meeting. And with that, I conclude my presentation, and I do not know to whom I need to give this for questions. Thanks.
Well, thank you very much, and I'd like to thank the team for an excellent presentation and really highlighting all the benefits of this mission. Now we go for the questions and feedback with the audience. I would like to ask the people who put up questions or comments to say your name and your affiliation. So as soon as we have the team in place, we will go ahead with this. So if you have questions already now, mark your hand up, and we'll then have a person with a microphone coming to you. Yeah, please go ahead.
Thank you. So my name's Antonin Knížek. I'm from the University of Oxford. I have two questions, really. Very interesting, by the way. So the first one is on the snow melting. So you relate this to flood risk, and you show how you detect the snow melt phase and all. But to assess flood risk, you probably need the volume of water that's released. So how do you get from the melt phase to the volume? That's one thing. And the other question is on the deformation. Because when you have volcanoes that are continuously active, such as Etna, I'd say there's a lot of ground monitoring stations around. And then for less active volcanoes, such as Santorini in Greece, for example, the changes in deformation are usually on the scale of months, maybe. And for landslides, it's on the scale of weeks, I should say. So how does Hydroterra, with the sub-daily coverage, increase the hazard and risk assessment?
Okay, first, so my name is Thomas Nagel. I'm from NVO and part of the MAC. Regarding the flood risk related to snow parameters, so Hydroterra is providing two parameters for characterizing the snowpack. It is on one hand the temporal evolution of the snow mass accumulated in one basin or in the region of interest, and this is done during the complete winter period. And using the same data stream, we also look for the start of the melt. The melting is actually determining the release of the water from the snowpack, and from this it has influence on the water management, but also on flood risks or on the conditions of the snowpack in overall. So we need both parameters in order to characterize, and Hydroterra is actually providing this simultaneously.
I'm Tim Wright from the University of Leeds. So in terms of the deformation question, really what we're trying to do with Hydroterra is fill that gap about the rapidly deforming processes. So we're not going to improve things on slowly deforming volcanoes like Santorini. That's already well covered by missions like Sentinel-1, etc. It's really about those critical rapid processes, for example, the ones that happen at Etna during that final phase before eruption. So I showed it, there was an example in one of the simulations of the 2018 eruption at Etna, and actually all the deformation happens within 6 hours, and actually no one's really captured those processes other than with very sparse local instruments. So actually to get the details of those processes with a kind of hourly evolution, I think is really transformative for volcanology. Similarly for landslides, I think, again, we're looking for those rapid final stages and those acceleration processes. But I think it's really exciting, the potential, particularly for this staring mode, for deformation.
Okay.
Highly hazardous on this stage as well. Careful.
Okay, we take another question. Yeah, in the back.
My name is Klaus Schmidt from German Space Agency. So first of all, congratulations to the team. It was a fantastic presentation, very exciting, and I think this is a fantastic mission. Nevertheless, we have here competition with we have to choose, or Archeo has to choose afterwards. And therefore, I always quote the famous Chris Replic question: what is the wow effect? What is the delta? Why is this mission needed? And why should we select this mission? What I have understood is there's a gap of sub-daily operational observation needs, and the mission contributes to global water cycle. But how can this be achieved if you have a very limited regional observation area with very representative sites, but still they are regional? And the question is, what does it matter on operational needs compared to maybe also improved regional observation networks which can be deployed in these regional observations and then can compete with satellite observations? This is question one. Question two is the sensitivity of atmospheric decorrelation effects was shown on a very, still I'm a geophysicist, but this is very back in the in early stages. Maybe I'm too stupid, but what I was missing was a statistical comparison with cloud maps, where you can show that the obvious integration effects on geostationary and heavily clouds are really taken care about and have no substantial effect. So this is more on the fundamental physics. But the real question is, how is an explorer representative to a regional observation area?
Okay. So thank you very much. My name is Harald Kunzmann, Karlsruhe Institute of Technology. I'm hydrologist and climatologist. So Hydroterra Plus, for your first question, will be the most holistic, comprehensive view of the water cycle that we have so far. And it is particularly on the interlinked variables that we measure simultaneously in sub-daily resolution. And the comprehensive view is important because in the meantime, we have very complex Earth system models which describe the entire Earth system, and we also need to validate them for all the different variables, not only temperature, precipitation, no, for soil moisture, for snow, integrated water vapor. These Earth system models, they cover the atmosphere, the land surface, the subsurface. And that is not only, let's say, important for the numerical Earth system model, it's also important for all AI models to come. Because we need the data to feed them and to train them, and then also in parallel to Earth system models to have opportunities with AI to do also better predictions. With respect to the regions, I'll start and then Antonio may take over. In all of these regions, we are in very close contact over all our research networks to comprehensive ground-based observatories that will allow us later on to validate what Hydroterra Plus sees from space, including even the Volta region in Africa, which I showed, because that is also particularly very nicely equipped.
Thank you, Harald. I'm Antonio Parodi from Cimo Foundation, taking over from Harald's message concerning the choice of region in Versailles. I can take over telling that those regions have been initially selected as representative of complex hydrometeorological processes spanning from water vapor to soil moisture, snow, and including also hazards. Those regions are climate change hotspots where we need those observations to cope with the complexity around predictability and predictive capability of those phenomena. But we have also potential to go beyond those regions in the sense that we are aware that there are in the visibility Hydroterra Plus area or the region of interest, and the time length of the mission is allowing also to explore other areas where we have other processes in place relevant and where we have already established connection with local networks and actors to make the full usage of Hydroterra Plus observations.
Yeah. Monti Guarnieri, I can answer to the second question about the propagation, the correlation of the cloud. So this was a really tough question. We do care about this because we know this is a problem. Fortunately, you know that radio propagation in medium has been studied by over a century because this drives telecommunications that are in ITU model. So what happens if in the cloud you do have water? It's clear that even in C-band, the cloud is opaque and in fact it backscatters. There is a recent paper in which there has been used Sentinel-1 data to estimate the rain rate by using backscatter from the cloud. Of course, this is not our idea to estimate backscatter from the cloud. We think that we are interested in the first part on the convection and not when the cloud is full of water, because you cannot have a penetration in this case. But in order to take care of this, of course, we have a lot of images of Sentinel. Also, we have images in dense cloud, and also this paper shows what's happening, and we do have a visibility of the terrain. So what we did in order to estimate the correlation, we take 1 year of meteorological model in all the conditions. We evaluated the integrated water vapor, and in particular the integrated water vapor in the integration time. I can say that when you think Hydroterra makes 1 image in 1 hour, that is not true, because in 60 seconds you have a resolution of 1-2 kilometers, and in 30 seconds you have a resolution of 2-4 kilometers. So the point is not really that you are a frozen acquisition. Of course, you're not, but in a short time, your acquisition provides a resolution that is enough accurate to retrieve an atmospheric phase screen that is evolving with time. So we really do estimate a fast evolution of the atmosphere that is not needed for meteorologists, but we do need to focus the image. So we did this statistics, we did this analysis, and I can say that even considering a very strong variation of water vapor in the space-time, that we know also for Sentinel and GNSS, the C-band is rather robust. It will not be the X-band, of course.
Hello, Valeria Gacheva. I was also presenting. Unfortunately, I did not really have enough time to present it, but as Andrea mentioned, the level 1 processing is adjusted for Hydroterra Plus. It's not the same as for Sentinel-1. And also, actually, during the system studies, we have put quite a lot of effort into looking into this, and also into analyzing the impulse response function, which is kind of the performance parameter of level 1 focusing. So we have already done quite a lot of work on this in phase 0. And also to mention what Torsten said, we'll have an end-to-end activity where this is, of course, also will be simulated in more detail.
Okay. Okay, one more. Yeah.
Okay, we just had one more response to the first question, actually, because it's a good one and it merits a thorough response. This one question that we were also discussing within ourselves, and we were sort of expecting it as a question, like, do these regional observations really matter on a broader scale? And the brief answer is that yes, they do. Because I think the key word here is the understanding of different hydrological processes. So having this holistic view at the same time of what happens in the atmosphere, what happens with soil moisture, what happens with snow, this will all improve the physical understanding of the Earth system as a whole. And this by itself brings added value.
Okay, let's go on. More questions from the audience or AGEO members? Markus?
Yeah, thanks very much for the excellent presentation. I have a question. I'm an atmospheric scientist, so I have a question regarding the integrated water vapor and the OSSI that you did. So you did discuss the synergy with some atmospheric measurements. What you did not discuss is actually the time-resolved measurements that we already have today, like from Sentinel-4 the infrared sounder, the cloud observations from Meteosat. So I was wondering if you already looked into that synergy and in how far that would change your conclusions from the OSI that your data product will really make a difference. Thank you.
Okay. Thank you for the question. It is very interesting and relevant. Indeed, we talked about this aspect in the sense that we are fully aware that there are other sensors already providing interesting observations. And we don't see the Hydroterra Plus like, let's say, an approach capable alone to solve all the problems, in the sense that it is going to fit one knowledge and observational gap which is present, in the sense that, for example, concerning MTG, we are aware that this sensor has a very excellent temporal resolution down to order of 15 minutes, more or less, but we are also aware that it is in some sense suffering a lot concerning the cloud thickness, in the sense that this sensor is capable to detect properly information about the cloud depth, okay, but not deeper into that. In this sense, we believe that a sensor like Hydroterra Plus with the integrated water vapor content is not competing with other sensors, but it is complementing, because having the possibility of having this information at kilometric scale and hourly time scale is helping to shape better the overall picture. So we know that there are other approaches available, but Hydroterra Plus can help a lot with the integrated water vapor content, especially concerning the initial phase of convection, the triggering, and also for example, the spatial organization of the integrated water vapor content, because there the gradients are very crucial in this variable, and Hydroterra Plus at the moment will be the only one capable to capture properly the spatial and temporal complexity. I don't know if you want to add.
Hello, I'm Vasiliki Kotroni from the National Observatory of Athens. We are working together with Antonio mainly on atmospheric processes. I would like to complete on what it has been already said, that we are aware that there are and there will be other measurements, but the Hydroterra Plus is able to provide at the same time integrated water vapor and soil, surface soil moisture that have not been explored up to now with our OSIs, and this is our aim to do it in phase A, where we hope to reach, because of course assimilating all available information will lead us to the final conclusions about the contribution. And I would only also like to say that we think that having in the same time integrated water vapor and surface soil moisture at the scales that Hydroterra Plus will provide, along with the other missions, and also leveraging with the possibilities of AI, will help us with downscaling and fusion, provide the 3D structure of many other fields that are needed for both physical and AI-based forecasting. But all this is for our future achievements and work.
Yep. Okay. Jonathan?
Yeah, I'm Jonathan Bamber, part of Accio. Just a follow-on question on IWV. On slide 93, I think it was, details don't matter. You showed that you had, so there's GNSS that gives you very high temporal resolution, but sparse spatial. You have Sentinel that is the opposite. It's high spatial, but relatively coarse temporal. And you have passive microwave as well. Now that is a perfect target for like present day AI algorithms to provide downscaling and relatively high spatial temporal resolution for IWV. So, I mean, it seems like potentially one can do this already with data that currently exists, at least for that particular variable.
Okay.
Peter van Oevelen, George Mason University. In general, I think the strength of Hydroterra is, as already mentioned, the consistency of multiple variables at the same time, which is unique. That consistency you don't have when you have multiple platforms. So no matter if you're talking about soil moisture, integrated water vapor, or others, having these things in one platform at the same time over the same region is unique and really help AI in actually improve our process understanding, for example.
In the meantime, we have already quite some experience in downscaling precipitation with generative adversarial neural networks. Downscaling really to minutes and kilometers coming from global fields. And I think it is these techniques that can be very beneficially applied also to downscaling that we are talking here about. So there is a lot of experience already gained in downscaling and using AI.
Okay, actually, we also have the option to have online questions from the audience. And a little bit following Jonathan's question here, there's a practical question here. I'll read it out loud on Jonathan's iPad. You have shown, it is from the Fabian Caminati at the Met Office in the UK. He says, you have shown interesting results where Hydroterra improved the heavy rainfall characterization. However, with integration time of 1 hour plus data processing and transmission, this may not be suitable for regional numerical weather prediction systems, either traditional or AI-driven. Have you any thought about sub-hour data availability for these numerical weather predictions? And I'd like to say this is, of course, a very practical application here of the Hydroterra. So it's not maybe the science.
I may provide an initial answer in the fact that as it is a coherence measure, as far as the path changes of fraction of centimeter, this is affect the focusing. So indeed, in order to have a focused product, you should generate maps of evolution of the integrated water vapor that are at a very short scale in time and space. So in temporal domain, you should estimate in 10 minutes, depending on the evolution, maybe even less, the variation of the water vapor. This is usually not assumed to be assimilated by meteorologists, but it's something that we need to compute to have a focused image. And so, yes, at least for focusing we do. We don't know how this can be useful for meteorologists, but we have it, and I pass the microphone to Tim.
Thank you. I mean, I guess two answers. One, of course, it's not an operational mission. We're trying to create data sets that solve and help us understand fundamental processes. But the advantage of being in a geostationary orbit is we can continuously stream the data down. So one of the delays, so already with Sentinel-1, we get data within about 3 hours, but a lot of that delay is waiting for the orbit to come over receiving station, particularly as we don't currently have the data downlink satellites available. So I think that will be very fast. I mean, over the course of my career, we've gone from ERS data, where we had to wait for the data to be shipped by tape, to MVSat, where it went on an FTP site maybe within a few days, to Sentinel within a few hours. And we're talking about technology here in 10 years' time. We'll be able to downlink the data very quickly. And I think for sure we want to be processing that and making products available as quickly as possible. We haven't really looked into how quickly we can do that, but I think we will want to do that as quickly as we can.
Okay. Okay.
Thank you. I would just like to quickly add that, okay, maybe you remember that I was presenting that there's actually a trade-off between the Asimos single look resolution and the integration time. So depending on which Asimos look resolution we need, we can choose the integration time accordingly. So if a coarser Asimos resolution is okay, then we could also shorten the integration time.
Okay, I think we go back now for the audience. I hope the online participant was satisfied. So we go down here. Yeah.
Thank you. Again, DLR, Peter Schad speaking. One question with respect to the observation regions. To what extent will the mission be able to look into the northern latitudes? Because, of course, the observation path through the atmosphere gets longer and the slope is different. So to what limitations will the mission have if they look to the northern latitudes?
Okay, thank you very much for the question. So during the system studies, of course, we focused on the performance assessment on our 4 areas of interest. Then we have also performed a preliminary assessment on northern latitudes. Antonio showed the full visibility domain we have defined at this moment, showing up to 52 degrees north latitude. At this latitude, we have assessed a preliminary attenuation of the signal-to-noise ratio of about 3 dB, like 3 dB moving from the center of the Mediterranean area to latitude corresponding to Copenhagen. During phase A, our idea is to further bring this assessment northern. Of course, we need to understand that we may need to relax maybe the signal-to-noise ratio, even if Valeria showed very well in his part of the presentation. Today we have a lot of margin to optimize performances, especially between noise equivalent sigma 0 and resolution.
Okay, maybe I would like personally to add a similar question. Now, when you have 7 years in orbit, maybe, or even longer, what do you do if there's an emergency in Africa? Do you have the pointing sufficient that you could go and look at southern Africa and not just northern Africa?
No, today the visibility domain is really from the equator toward the northern hemisphere, because for the subdaily interferometric capabilities, the inclination of the orbital plane is really targeting the northern hemisphere, so having the reference target like in the middle of the Mediterranean area on the same orbital plane as the satellite.
Okay, very clear, thank you. Yep, Jonathan?
Yeah, can I ask another one, if I may? So you've mentioned it's not an operational mission, it's not a monitoring mission. It's what you want to do is have some better understanding of certain processes by the end of this exercise. So can you just clarify what we will be able to do, what we will understand, where we will be at the end of this, let's say, the 1 year slots that you have for each of these regions that we can't do now? So where will we be? What will be the scientific advance that this mission will give us, rather than, like, I don't know, seeing Etna bubble away or something?
Yeah, I'm Luca Brocca from CNR, Italy, and yes, I'm a hydrologist. And being a hydrologist, actually having this kind of measurements collocated in space and time at 1 kilometer 1 hour is it will be really the very first time. So giving a full answer to your question is difficult, because it's difficult to have a full understanding of what we can achieve with this kind of measurements. But for instance, if you want to spot some important knowledge gap that we have now for the hydrological cycle, one of them is, for instance, the interaction between the land and the atmosphere in over agricultural area. Irrigation is playing really a major role in driving the water cycle in those areas, and we don't have observation of irrigation. From Hydroterra Plus, we can have, for the first time, this kind of measurements. Similarly for snow water-related dynamics. Over the Alps, we have measurements only over some stations. We don't have any other kind of measurements. And with Hydroterra Plus, we can really reveal the sub-daily cycle of snow water equivalent over time. And even in 1 year, actually, we have a density of measurement in space and time that can really reveal something that we don't know currently. So, for instance, how much snow is needed to accomplish the water uses for the Po Valley in the summertime. Currently, we have a sparse measurement, and we don't have a full picture of this. Hydroterra Plus, for the first time, will give us this full picture.
I'm just going to respond to the Etna bubbling away comment. I think the key is it's not just about making some observation. Okay, here's another eruption. It's about those final stages of an eruption. We don't know. Volcanoes swell all the time. Some of those go on to erupt. Some of them don't. We really don't understand what it is that we could measure that would tell us whether a volcano is going to erupt or not. And that matters not just for Etna bubbling away, but if you live in Naples and you've got Vesuvius there inflating, is that going to erupt or not? We had an episode in Santorini last year, 2 years ago, where we had a big inflation and deformation episode. Didn't lead to an eruption, but it did lead to evacuation, etc. So actually understanding what it is about those processes that we can, what can we observe that would help us do that? And I'm not, it may be that we don't know, the data don't solve that problem, but we need to make the observations before we can constrain those models.
I understand all of those points. They are all local. So Etna behaves like Etna behaves. All volcanoes have their own kind of dynamics, more or less. Your irrigation example, again, irrigation, that's a very local kind of process. So is snow melt dynamics for a particular catchment. So, I mean, what are the fundamentals you're going to learn here that you can then apply to, every hydrological catchment on the planet?
Okay, I think Hydroterra, with this common view to multiple parameters, addresses primarily also water management. So, of course, we are observing the Alps, and we don't have sub-daily observations currently, which helps us to assess the current state, but also to improve the forecast models. How can we use the water which is available in the Alps? And it's not only affecting the Alps. Downstreams of the big rivers, which are all originating in the Alps, it has also an impact. Currently, we have this problem. We had, for example, a lack of snow of 30–40% in comparison to the previous years. And this water is also causing low groundwater level in many countries, not only in the Alps, but also outside of the Alps. And this, of course, to manage these resources, to know how much water is stored, how in the snowpack in the Alps, which comes maybe not now in the wintertime, but later on during the snow melt, and also to know through the snow melt phase product when the water starts melting and when this meltwater is coming. This helps, of course, for managing these resources. And it has an impact also on the soil moisture itself, but also on many other issues. So it's a kind of integrated view to the water management. And we can learn from this. We can export this knowledge, what we are gaining, to other regions in the world. But of course, we are primarily observing this.
Let me conclude maybe again with the wider picture, again, summarizing what was said already. We have dramatic changes in the water cycle. As I said, now we have 30% of Europe is under drought. In Germany, we haven't had droughts till 2050. Now, even in the alpine regions, we have snow droughts. We don't have rain for weeks in March. We have declining groundwater levels. We have to fight, on the other hand, with more and more flooding and heavy precipitation. What is needed, also according to Conference of the Parties, to Davos, for national water strategies, we need to be better prepared. We need to go for anticipatory action. And that is only possible with science and evidence-based knowledge. And that is what we are proceeding here, this scientific understanding. And we will have unique data sets to learn much better and to achieve all the basic knowledge for anticipatory action. And that is of high societal relevance.
Okay, thank you. I think we'll take a last question, maybe from a broader audience. So one last question. We have 2 minutes to go. Okay, it's let me just take anyone. It's your last chance. Not being from, yeah, they're coming, okay.
Thank you. Maybe just a quick one. So, what are the climate projections for the amount of snow in the Alps? Is it eventually going to disappear?
Okay, so I'm quite convinced that when the mission is launched in 36, we will have some snow. But of course, the snow dynamics are changing. So we observed this in the last years. So what we had 30 years ago was the extreme melt events during the high winter period in December, January, like this. So the dynamics of this snow accumulation versus warm periods with snow melt, also up to very high elevations, up to 2,500, 3,000 meters. This is changing quite rapidly, and this was not the case in 30 years ago. And I expect actually that these climate variations will continue or even will be stronger in the future. And these high variations make the need to look for these quick observations, these periodic observations, even on the sub-daily cycle.
Okay, we'll take that. Okay, well, we have one more question, and one last question then from NASA online, but I cannot see the online, so could you read the thing? Okay, this is from Craig Ferguson at NASA headquarters. It is known that C-band SAR is sensitive to changes in vegetation water content. Why does Hydroterra Plus not investigate sub-daily changes in vegetation optical depth to potentially contribute to our understanding of short-term vegetation, water, and heat stress responses? Yes.
Yeah, indeed. This is a very interesting question that is also known from Sentinel-1. So then product of soil moisture that is today operational from Sentinel-1 measures the soil moisture, but a part of it is the vegetation water content. So it's mixed in the product. So the outcome is a proxy of the soil moisture variations. And this is operational. Now with Hydroterra, we will be able to do this in a much more frequent time, so then not only the 6-day revisit, but then this hourly revisit is a factor of 24 more time resolution. And on top of that, what we have is the phase information that is not used, that in Sentinel is very difficult because of this 6 days revisit, you lose the coherence. With Hydroterra, we have this 1 hour. So then we can use the coherence to get additional information and try to decouple this water content of the vegetation from the soil moisture. And this is something that we have already campaign data, we have also ground-based data, and we are going to investigate in the phase A.
Okay, thank you very much. We'll close the questions and answers. I'd just like to say, Thomas, especially thanks that. And yeah. I just tried to say, Thomas, even though ESA is slow in potentially launching a satellite like Hydroterra, it's good to know that in 10 years we still have the snow in the Alps. Okay, we convene again at 1:30, and then it's Keystone.